So I just want to say this is mainly a filler presentation because we just, we all had other stuff to do this week, and I had this presentation prepared maybe a few months back, and it's a presentation that's just full of speculations and a lot of my intuitions that could be wrong. So I just want this to be, it's not really an actual proposal, but more of a casual discussion. It could be distracting because it's not really targeted at problems that we're trying to solve at the moment, like actions or like layer 5 outputs or goals or things like that. So
I mean, it's related to voting, isn't it?
it is.
Which is something we've been talking about recently.
Yeah, but it's a slightly different way of thinking about it. So
the words are, you see, warning us, the words are familiar, but they're going to mean something different. Is that
there might. It's trying to achieve the same goal, but I just maybe thinking about voting slightly different. So yeah. Okay. I'm going to be touching on a lot of topics that we've discussed before, and some that maybe we haven't, like spatial pooler, temporal pooling. But also I want to start from how we do things in Monty, and get started from there. So
I don't know if it's worth, just for context, at least when we briefly discussed this, the two of us, my understanding was this kind of shared learning and voting primarily relates to when there is like a fixed offset between sensors. And so I feel like that's useful context, because that means it could be complementary to what we've been talking about recently in terms of a series of movements that might send 5 key locations or 5 key displacements, and all that stuff that was discussed in London.
So maybe
so I think what you're describing isn't necessarily going to say do this instead. It would be more like, okay, if that's for where there's arbitrary spatial arrangements, what do we do for all the columns, potentially hundreds, thousands of columns that have more fixed arrangement?
Are we talking about like in the retina where they have a fixed arrangement?
Exactly.
Okay.
Or along a finger. Yeah. Is that fair?
Yeah. So Jeff brought this up before, this topic about independent and semi-independent sensors, and this would be for the ones that are like semi-dependent, or like they usually the locations are kind of like fixed between them.
Right.
The location in the world may change. So even if the locations on the retina they have fixed arrangements, the sensor module might actually send the location, because the sensor module has depth. So it's not just as simple as having all these arrangements fixed on the retina, because there is depth to it. And
what you're saying is they're fixed on the retina, but they're not fixed on the object.
Yeah.
Right. So this is again, I'm saying, well, what would be a situation where they're fixed on their? Well, I mean, it's great. Always think about it. Yeah.
Well, when we're looking at a mug or something with the depth, the location that's actually going to. So the retina is just like a 2D arrangement of the objects, but it doesn't really have depth. So the locations might actually be, the locations that include depth have more information to it. Like if we want to vote, we still need some kind of information, location information that includes depth in it. It's not just a.
Well, yeah, I'm just wondering what would be if there's a biological situation where this scenario would count, where the scenario you're about to discuss would be valid. Like, so if it's not the retina, because the retina they're not, because you've got depth information.
On the skin, I guess you have very definitely nearby sensors on the skin, and they'll always be nearby.
Right. Well, that would be like, it wouldn't be an entire finger then. It might be just one digit of a finger, something like that.
Yeah.
Some part where the body can't really change.
Yeah.
Okay. Well,
and I guess what you're going to discuss, Ramy, might be able to accommodate some of that change in, right? Yeah. I think what you're saying is it doesn't need to be totally fixed. So it's somewhere in between a proposal that just takes 2 fingers on 2 different hands, totally arbitrary, and assuming like totally fixed.
Yeah, I might be able to handle some of this depth issues when we're doing voting and sharing.
Okay.
All right, so I'm going to start from Monty and talking about unsupervised learning, because I'm going to try and frame this from a problem that I think we already expressed before when we're dealing with learning behaviors. And I'm going to frame it from unsupervised learning. Let me first explain what unsupervised learning is. In Monty, we have two types of experiments that we run. Usually, the one that we run most often is the supervised inference, which is basically we do supervised learning first, and we form some object models, and then we use those models and later do inference by initializing the hypotheses, because we already now have the models, so initialize hypotheses, and then we try to match and figure out which models can explain these observations that we're seeing now with the sensor. And this is more of a matching phase step. With unsupervised learning, we already have a pipeline that's also working and that's also good. We just don't run a lot of experiments with it. But what this includes an extra step of, in addition to matching, we also do exploration. And so there's always this going back and forth between matching and exploration. And basically, we first try to infer the object. If we're able to infer the object, then we improve it. If we're not able to infer it, then we create a new object or create a new reference frame and then store all these points that we've seen in this reference frame. So I'm going to go through the process, the pipeline of how we do this, and then we can go on to why I think this might be a problem for behavior models, or it may not. I don't know. We'll discuss this. So this is a regular step in like Monty. We get some sensory inputs. And what we do in unsupervised learning is we try to infer the object. So this is assumed to be in the matching phase. We still haven't inferred the object. We try to infer it. If we're able to infer it, then we try to improve now the model by going into exploration phase. And still, the output will always be just an action. Continue to do the sensory motor loop. But we are improving the model now that we have already inferred. So we're not creating any new models. We're just adding to the model that we inferred. But if we haven't inferred the model, this is an additional step that. So if we haven't inferred the model, we check if we have reached the maximum matching steps. This is something that maximum or minimum. It's just a number of steps that we just make sure that we want to have a minimum number of matching steps before we move on to creating a new model. So we check if we have already finished all the matching steps that we have, and we create a new model, and then we add all these observations into that new model, and then we continue to improve it with the exploration steps. But if not, we continue to do more matching steps. And every time we do a matching step, we're storing this into a temporary model, which is called a buffer. And once we infer the model, we add all of this information in the buffer into the model that we inferred or the new model that we created.
And I mean, another important check before we create a new model is that all of our existing hypotheses have negative evidence. Like nothing we know about matches the current sensory input.
Yeah. And there may be a lot of details missing here, but I think this is like the high level overview of.
I'm just highlighting that because I feel like that's a lot more important than checking if we did the maximum matching steps.
Yeah. Okay.
Like we only create a new model if none of our existing models can explain the incoming input.
That's how I interpret it. And also I assume that it was like, hey, we keep trying, and then at some point you say we tried too much, and now we have to start something new. That's what they're meant by this, right?
Yeah.
We're trying to match something.
We try to match it. We have to finish the matching steps, but also we have to make sure that none of the observations or none of the evidence is high enough. And if that is
right, got it.
Okay, so let's talk about.
Actually, if we reach maximum matching steps and there are still several possible hypotheses, we wouldn't create a new model. We just say this episode there's nothing learned.
So this is the correct MLH?
Yeah.
Yeah. Yes. Yeah, I recently came across that in one of the tests. Yeah, I agree. So we basically need to, it needs to be confused, totally confused about the object, and that we create a new model. If it's not confused, and if it thinks it might be some of these possible, like if it's possibly, if there's some evidence high enough but not high enough to cross this threshold, it will just, what you're saying is that it will not do anything, right? It will not improve the model, or it will not create a new model.
Yeah.
Okay.
Yeah, which I guess is its own kind of interesting thing to maybe think about in the long term, because it feels like,
well, I mean,
like there'll be instances where you kind of, I don't know, you don't match to an existing model, but maybe it's sort of close to some existing one, close enough that it doesn't have negative evidence. And then, I don't know if, like I can see why we have that heuristic, but I don't know if that will limit our ability to create new models.
I mean, the maximum matching steps is really more of a quick little hack to keep our experiments from running super long. In like nature, you don't suddenly have your brain say, "Oh, you can't do more now." You would just keep exploring until you figure out what it is or that you don't know it.
Well, that was occurring to me. There's a bunch of other things that are not included in this. You know, like sometimes like it just doesn't include the deformation stuff we're talking about, because you may not match, but sometimes we're going to match by doing the dimensionality reduction we talked about. So that's got to be part of this too, I think, at some point. And then also, I was thinking, what do we really do when we're looking at something that's confusing? Well, then we'll look at some details and see if we understand the details, or maybe we zoom out and look at the bigger picture, like what else is around. So the actual process of overcoming confusion in a biological organism is more complex than this, involving attention and I don't know what, but we never really sort of tease that all apart. But it doesn't mean you can't understand a subcomponent like this. But this isn't the whole thing. There's more to it when you're confused. There's more to it than this.
Yeah, and this is not. Sorry, go ahead.
It's just kind of in some sense, it's just like if we have a lot of prediction error, then we probably need a new model. Or if we consistently have high prediction error, and I guess that's kind of what the heuristic about all our models having negative evidence is kind of capturing. But yeah, you can imagine something like maybe when you attend to something, that might amplify prediction error associated with that, and increase the likelihood that you decide to learn a model or something like that. So that if someone hasn't pointed something out, or if something hasn't caught your eye, that's not really going to drive you to say, oh, okay, I need to now learn about this. But if whatever reason that's kind of salient, then then it does feel more likely that you start developing new models for it.
Yeah. Okay. I'm going to talk more about this part here, where we why in behavior models we may not be able to infer easily as we do with morphology models, and why that may cause us to go into this branch more often. So So consider a behavior model. Consider some behavior. This bird is flapping its wings, and we're trying to learn this behavior. So during learning, we are now we start in the matching phase, and assuming that we're starting from scratch, we don't really have a model, and we're now just trying to learn this behavior. So what we're storing here in the reference frame what we're storing here is locations at changes. And that is also stored over time. So as we go from one observation to another, there are two things that are changing. The object itself is exhibiting some behavior, and this changing is moving, but we're also changing the sensor position.
Well, that's an assumption we haven't really we never really dealt with how we learn behavior models. Remember, it's very complex, right? We don't really have time to move the sensor all the time to all the different changing locations. Remember, we kind of, this is an open problem how we learn these things. So I don't want to get sidetracked here, but But how we learn behavior models is pretty still an open question as far as I'm concerned. We kind of have an idea what they look like when they're done, but how we learn them, I don't know. Do we move our senses? Sometimes I don't have time, there's multiple things moving. So how do I can't attend to everything that's moving at once, just remember that, right? Like there's multiple edges on this bird that are changing, not one location, not one thing. And so how do we attend to all of them at once? It can't. So anyway, it's an assumption. What you just said there is not 100% understood that we're moving or attending different locations. So, but we can keep going. But already,
I'm targeting this problem specifically, and I think that maybe what I'm going to propose, or what the ideas that I'm going to share, maybe we can get something useful out of them to help with this problem.
Okay.
Because I think this problem can be solved with shared learning if every column is not only considering the hypothesis that it comes up with based on its observations, but also looking at the neighboring.
Well, that's good because in some sense we deduce that because we don't have the luxury of time in learning a behavior model, that we have to do shared learning. That was sort of like, how else could you possibly do it, right?
Exactly.
All right. So, all right.
Okay. So, so the problem is understood, but just let me just go through the problem again so that.
All right.
So we're here, and as we move the sensor and the object moves at the same time. So we basically start building, when I have these pink dots here, that's just basically saying there's no movement, so we're not really storing anything here. There might or might not be, it's just an example. But as we keep moving like this, we're storing those changes at these locations. And we've learned a behavior, right? These are all observations. We've created a new behavior model, and we put these observations in the reference frame. But then after that, if we observe some other behaviors, and then we come back and we try to, we're seeing the same behavior, but now we're trying to infer it so that we can improve it. And the problem with that is that if we start sampling different, because we don't have the luxury of time, like Jeff said, we may not actually end up getting any observations that resemble what we have in the model. And so the hypothesis that we create and everything is just not going to match very well. And we don't have the luxury of time. We don't know where to start from. I simplified the problem here by saying, okay, we're starting at the beginning of the behavior, but we don't know where it's starting from. We don't know where we need to, like spatially or temporally. We don't even know what the object ID is. So it becomes a very difficult problem to infer the behavior first and then improve it.
Well, I mean, the real problem, again, stating what we just said a moment ago, the real problem is your first row of boxes there is not the behavioral model. It's a subsampling of the behavior model, right? Because the behavior model, in the way we've talked about it, it includes all the places, all the parts of the object that are changing. And this is just one subsample of that, right? And so it's like, it would be like saying, I'm learning a coffee mug, but I've only learned 3 points. And now I come back and I check another 3 points. It's not going to work well. And that's what's happening here. We didn't really learn. Go ahead.
If during learning you see the behavior repeat over and over again, and you know when it repeats, and you basically have the luxury to move to all the different locations while it's repeating, then the top row would have like Jeff said, a bunch of different changes at different locations stored, and then the inference wouldn't be that big of an issue anymore. But that's an issue.
So to me, it's not an inference problem. We're describing it's a learning problem. We don't know how to learn. We don't know how to learn this behavior model, and the first row there is not really. It's just a small subsample of the model.
Yeah.
Right. And that's mostly because the object itself is moving, it's changing in time. We don't control this movement.
Well, it's more that it's just that there's multiple parts moving, and a single column can't observe them all at once.
Right.
Right. And may not be able to attend to different parts. So it's a real, we have this beautiful idea how a behavioral model might look, but we have a very poor idea how it might be learned. So hopefully you're going to get to the point of like, we're going to have to learn differently, right? We have to come to shared learning. It's really, it seems to be the thing. Yeah. So I don't think it's an inference problem. You're describing it. I would say we can't infer this. We have a learning problem.
But if the bird wasn't moving, if it was just this first frame for all of the rest of the frames, then we'd be able to go and over time just collect as many observations.
Right.
That's learning. I guess you're, I think, emphasizing inference because you opened with unsupervised learning, where we have to infer the object first. But I guess, I don't know. So it's maybe part of the problem that like it exacerbates the fact that like if we don't have a behavioral model to begin with, but it feels like maybe there's ways of working around that. Like, I don't know, again, going back to attention, if you're just deciding, okay, now there's a lot of movement here, I'm going to learn a behavior model. I may not need to constantly be recognizing that model, or it's enough to know that I don't have a model, and I'm going to start learning one. And then once you do have a model, then we can use stuff like voting to help do inference of the behavior. So it feels to me like the fundamental issue is the learning one, is the kind of shared learning and how we access all that information.
No, I agree. Yes, I agree. If we're not able to learn well, I think this is just the next step. If we're not able to learn well, if we don't have a good learned behavior, then we can't really infer and improve the model later on.
I mean, learning and inference are hard with the behavioral model, but we should start with learning. Really, that's the harder problem.
Yep. So we do actually have when we're learning morphology. So even in morphology, when we do supervised inference or supervised learning, we add some supervision, and that supervision is it's basically supervising. It's like we have a viewpoint here, and then we move the object like 14 different rotations, and we know the difference in rotations or difference in viewpoints. And then we also supervise the object ID. We tell it what object ID we're looking at here, so that you add it to the correct reference frame. And I think with behaviors, we can still do the same supervision thing. It's just going to be we're going to be supervising one more thing, which is the time. So basically, where we're starting, we need to supervise that. We need to supervise the location on the object, or like the viewpoint of like where we're starting to look at the object. And
are you talking about a morphology model now?
I'm just saying that in the behavior model, we can do the same thing that we're doing in a morphology model to learn in a supervised way. We just have to supervise an additional time variable here. We just tell it, okay, we're starting this new behavior. This is where we're starting from, so that we can store the observations correctly.
It's interesting because it's getting a little bit crazy when I'm not even let you get to the point of your talk, but when we think about the temporal memory algorithm, it works from anywhere. It doesn't have a start. I mean, it can start. It does have a start, but you don't have to start at the start. You can start in the middle. Like if I learn a melody using the temporal memory algorithm, I can start playing the melody in the middle, and it'll still infer the correct melody. That was one of its nice attributes. And so I assume something similar is happening here. That in this case, we have a cyclical behavior, like the bird flying, which is unlike the stapler, perhaps. I would assume that the behavior could be inferred starting anywhere. It doesn't have to be supervised because it's a sequence. Yeah. It's a sequence of patterns.
Inference can happen at any point in time, but I think what Ramy's mentioning here is if, like, the way we were planning to do the first test of behavior models is to supervise learning in order to avoid this issue of only seeing one point at any point in time, basically telling it, okay, this is a behavior. Now it repeats. Now you're at the time point in the behavior. So you have the time basically to move to other locations and know
where in the behavior sequence you are. This is a sort of an implementation detail of how we would do this in Monty, something like that.
Right. This would be the way we would be able to learn a complete behavior model to then be able to test inference on that behavior model. And that inference should then work by starting anywhere within the behavior.
I see. Sorry.
Sorry. If we have enough points, then we could do inference because we can now create a hypothesis space that's big enough to start anywhere in the sequence and at any location.
Got it. Right. So this is a kick. This is a way to kickstart training or get training going. I mean, sometimes, like, you could argue, the stapler has a default position, and it could start from there, maybe. You might argue that birds might have that too, if you run before they're flying and they're sitting on the beach, and then all of a sudden the wings go up, that could be the beginning of the sequence, something like that.
Yeah, okay, and we talked a bit about like what could be potential ways the brain infers when a sequence repeats. And for example, one option could be is when the canonical morphology is inferred. So like when you recognize the closed stapler, that's a signal that maybe now it's back in the starting state.
Interesting. We had the same problem with the temporal memories, is you don't know when something starts repeating, you don't know if that's part of a longer high order sequence or if it's just a repetition. You hear the refrain again in a song, and is that just the same song starting over, or is it just a refrain occurring in the second, section of the song, and it's going to continue on? So there's always this problem. It's the branching problem, right? Is it? Are we done, or are we just continuing on in a higher order sequence? We never resolved that really well. So we have the same problem here, perhaps, with the bird. But you're assuming there's maybe a canonical form that we get back to and say, okay, we're done. But it could be that stapler bounces down twice, and then the third time it rotates. So then you'd have to say, oh, it's like 1, 2, and 3. But all right, we can go with this for now.
Yeah, but I think it's an interesting idea that we don't have to infer all these things at once. If we figure out first what behavior this is, or if we figure out first what this object is, then maybe we have stored some location to always start from on this object. It could simplify the problem. We just maybe go to try to figure out where that location is, and then start the sequence from there, or wait for the behavior to get there and then start there.
Okay.
Yeah. So the idea here that I'm thinking about is, I think we all thought about this with the shared learning, is that maybe it's not enough that if we're looking at this part of the object whilst doing the behavior, it's not enough to just focus on this part, and that there needs to be some kind of sharing information between the columns, such that what we're really learning about the behavior is not only inside the column, but also coming from the neighboring columns. I don't know if I phrased this correctly, but at this time step, you would need to, this column needs to be aware of some of the things that are happening around it.
Somehow, I think we can all agree that you couldn't learn a behavior like this looking through a straw. It's just too hard. It's hard to learn a static object looking through a straw. So somehow we have to integrate the input from multiple columns at once, is what I think you're saying. How to do that? You're going to propose something, but I think we can all agree that yes, this seems to happening.
Yeah. Okay, so I'm going to switch gears a little bit and talk about voting, and then come back, because there are a few topics that I have to talk about first, and then come back to we'll come around to this idea.
Just looking at this bird picture, every column that's looking at anything moving would be active, and so in the case of the bird, and we're not talking about the bird moving through space, but the wings. For example, there'd be a lot of columns that are actually it's not just 4. It's not like 4 locations, right? There's a lot of points here that are moving depending on the receptive field size of the columns. So this is it's not a one of 4 columns. It could be 50 or 100 or 1,000. We don't know.
And just to play devil's advocate, I guess the other option that we talked about before was that we don't have shared learning, and you basically only can learn it by a lot of repetition that's kind of self-control, like a child opening and closing something over and over again. And then maybe for things like the bird, some of these behaviors, like something flapping open and closed, can be applied to the bird that you've learned by controlling it over and over again. Because, you can't control the bird, of course, but maybe it is possible to learn it through a straw if you're able to control the object and do it over and over again.
It may be theoretically possible. It seems like you'd have to know exactly where you were in the sequence, right?
So you either need to be controlling the sequence, like opening the stapler and closing it yourself, or you need some kind of signal, like a click when it repeats, or if you have flash inference for morphology, like through voting, you could recognize a canonical shape or something when it repeats. But yeah.
One thing I'm also just wondering about now is with like a higher level column that's receiving kind of a larger receptive field, a coarser input, whether if kind of learning happened there first of behavior, it would be a more primitive model, but that might help kind of lower level columns to kind of recruit them again. So just in the case of this bird, if you just kind of had like, oh, there's like the flow of a wing, which is just like a broad area of movement up and down, up and down, up and down, then like that could be learned more easily because there's not that many locations.
I would think that's possible. But I would think it's, we talked about in the beginning with the stapler that very quickly you decide that the stapler top is a child of the stapler itself, right? And so even though you're observing all these edges moving, it seems like what you're really learning is the rotation of an entire child object, which is a simpler thing to represent. So, I mean, you just suggested something, Niels, which is like, oh, we could use a fuzzier image. Maybe, I'm not saying that's wrong, but it feels to me the more powerful mechanism is to take all the little movement bits that are representing the stapler moving, which are all along the edges of the top of the stapler, and turn that into something. Oh no, we're just moving one thing. The thing that's moving is this whole sub-object of the. And we worked through some of this, but I don't remember the details that we did. But
yeah, that's maybe similar to what Niels is saying. Only that instead of having a coarse resolution sensor that feeds into it, you have a learning or several learning modules that do voting on the morphology and its orientation, and that becomes input to a learning module.
I'm getting confused. I'm sorry.
Like you can do flash inference on morphology, like infer the bird or infer the rotation of the wing, and then that inference could be the input to another learning module that models the behavior, and it learns.
Oh, okay. Well, that's right. So right. So as long as we're agreeing, we're doing a compositional construction of the behavior, right? It's just like we don't, it's inefficient to learn the complex morphology of an object. It's much more efficient to learn it as a reassembly of child objects. And so the same thing I think we're saying could apply here. We're saying instead of learning the complex behavior of this wing or the stapler top as just a bunch of edges and moving in different directions, we can learn it as a compositional structure of some child objects that have simpler behaviors as part of part of a parent. Is that we're both talking about the same thing?
Yeah. Okay. And I agree. Yeah, it would be nice to use compositional models for that, and I guess it would, it would make it easier to learn the models in the first place at the higher level one. But then I guess through hierarchy, maybe that could also help because we probably eventually do want to learn a more detailed model like this if it's an important behavior that we keep looking at.
Well, it would be detailed in terms of the stapler. It would be very detailed as long as the child object at the top of the stapler is modeled, right?
I guess I just mean with kind of the local features. But what I'm trying to say is that the higher level column that's learned the compositional behavior could tell the lower level column, you should be seeing this behavior and you should be in this state. And that would help with this issue of like, how do we where's this supervision coming from that's telling a column this is where you are in the sequence?
Well, we talked about the parent telling the child what they should be observing, but in the case of the stapler, the child object is not observing a behavior. The child object is moving through space, but it's not changing.
Yeah, I guess I'm describing a different arrangement, which I don't know if we'd want, but it's a behavior, being a child of a behavior. Basically, but if one behavioral model is more fine grained and another one is more compositional, more.
Well, maybe I don't know.
Of course,
maybe we should.
But yeah, I can't think of what the advantage of that in a feed forward way would be, other than maybe inference.
But I guess the point is that there are some tricks we could leverage besides shared learning, like doing flash inference on object and pose, and then learning a compositional model of the behavior, or
looking at the object many times, as you say, controlling
sequence.
it. Yeah.
I mean, remember, it's like, the logo that Ramy did, where the logo exploded in 4 different directions. That was really hard to learn, right, as a single behavior, because you had 4 things going different directions. Where the stapler is easy, there's one thing that's moving. So it's like, I guess what I'm trying to say is that it's much, much easier when we break these down into simple parent-child relationships. Maybe we should just table this and try to store it in our memory while Ramy goes forward. Because we don't even know what he's going to propose yet. So
I'm just saying that, yes, a compositional could help, but some examples may not be clear where the composition is. For example, like if I do like a pencil, if I keep doing like swinging it like this, then if you just have one column, that's
not clear. That's not clear to me. That's the behavior. That's
a behavior.
I'm not sure it is. It's an object that it's only behavior if I include your hand in it, right? The pencil itself. Remember, we've been through this argument. A pencil itself moving through space is not a behavior, and we try to make that clear in our London offsite. But it's a behavior is when an object's model is changing, not the location of the object in the world. So if you're just moving a pencil around, that's not behavior. If you're talking about the way you're manipulating a pencil in your hand in a particular way, that could be behavior, right? I want to make sure we get our language. We agree on the language. If we don't agree on the language, we're going to be hosed here. So
yeah, I wasn't talking about like moving the objects like this or rotating it.
But even just holding it in your hand, moving it in your hand, it's not a behavior of the pencil. Unless it could be a behavior of your hand and a pencil that when you put those 2 together, they behave in a certain way. But because the parts are moving relative to each other, but just moving the pencil around, it's not a behavior of the pencil. I mean, I think we either agree about that, or
I think the one context we said it could be would be if you are learning it kind of superimposed in some sort of like imaginary or blank reference frame. But basically, there always has to be like some sort of parent,
right?
So you can imagine you're learning the pencil kind of pivoting about a point in space, but the point is there's still a kind of a parent in that context,
right? It has to be
without a parent. It's just an arbitrary movement in the world.
It's just a location change or a pose change, whereas it has to be behavior has to be relative to some larger reference frame, right? That's what you're saying.
Yeah, maybe the movement of the pencil is too simplistic, but if I like squeeze the water bottle from like here,
well, the squeezing it right because the water bottle's morphology is changing, right? Where the pencil's morphology is not changing. So in this case, where the morphology of the water bottle is changing, sure, that's a behavior. Or the lid's unscrewing, that's a behavior.
But then it's not very clear, how compositional models would help us with the squeezing of the water bottle, because it's like a deformation of an object.
Well, right. I kind of threw in a moment ago, like, some of these things all wrapped together, like we started talking about inferences. Yeah, we have to start thinking about inference of deformed objects as well. Right. So we don't have good answers to these things yet, but there's a bunch of overlapping things that we've been dancing around here. So, right. Well, in the water bottle, you could say there are features of the water bottle. I mean, there's edges. These are point normals, or on the water bottle, and their location relative to the water bottle are moving. And that would be that's a behavior, right? It's anytime you have a features, you have a morphological model. It has like a structure, and when any of those features change in any way, pose or ID, that's a behavior.
Yeah.
So,
and to learn this behavior, we may not be able to utilize compositional models. We have to just learn the behavior of the water bottle as well.
Right. Well, like the water bottle is a good example because there doesn't seem to be a child object that I could pick out from that. Right.
Right.
Whereas
the balloon is the classic.
Balloon is the balloon. I've now learned a sort of negative reaction to the balloon. I don't know why it is. It's like scratching on a whiteboard or something. Balloon. But right, the water bottle is a good one. It's very much like the balloon, right? It's pretty much the same thing. And it's not clear what the compositional structure of that would be. Whereas the top of the water bottle definitely has compositional structure, and even the bird and its wing would be compositional structure, right?
Yeah, but within the wing itself,
the wing,
different changes.
Right. So there's your complexity. The wing itself may be changing, but its position relative to the body of the bird is definitely changing.
Yeah, and I guess just to go back to the early thing was just that like there could be some amount of like global flow that higher level behavior models could also be learning that could be helpful in this. So with the water bottle or the balloon, like that could be like a simpler behavior. But yeah, I think anyways,
Yeah,
no matter what,
assume
this might be helpful. So
but I get your point. There needs to be something that is larger receptive fields, whether we're getting it from multiple columns or we're getting that from another column that is getting larger receptive fields. And it needs to
well, that's not the point I was making. The point I was making, it needs to be a reference frame. You have to have two reference frames for behavior, something that's moving and something that is moving relative to.
But I mean, you can also have behaviors at the lowest level of the hierarchy.
Well,
as in like behavior that's based on moving, like optic flow, just direct sensory input.
Well, I guess since that would be, let's say I only have a V1 and I'm looking at the water bottle. I mean, there's the water bottle's reference frame, and then there's the feature that's moving relative to it. So maybe I misspoke when I said two reference frame. The feature has to be moving relative to the
right.
And the feature may or may not have a reference frame. If the feature is coming from another column, another region, then it would have its own. It's its own definition. But if it's coming from the retina, well, in some sense, it has its own structure and definition too. It's an edge at some edge orientation. All right, we're getting down the weeds here.
Okay, I'm going to continue.
Yeah, those will never get done today.
Okay. So, like I said, I'm going to switch gears and go to voting and talk about how we do voting today. So the way that we wire up voting and use it is that voting is an inference process. And what I mean by that is that we have, if you look at these here, I'm imagining three columns. There's one maybe on the phobia, and then there are two other neighboring columns. And we're just saccading and moving on this object. And what I mean is that these columns, they each build their own object ID, their own model, their own reference frame with features at locations, and they're independent, completely independent of each other. And after we're done with learning, we would start associating these object IDs in layer 2 and 3 between the columns, so that we're now, and I'm only talking here about voting on object IDs, but the way think about this is that this is an association between the final object IDs after learning, because now they're stable, and then we can start forming the associative connections between them. Okay. And
I guess, I mean, wouldn't we be forming associative connections during learning? I mean, yeah, we first have to realize that that they are sensing an object, but
well, the question is, when does unique ID form in layer 2 and 3? When does that occur? If it occurs right from the start, then they could be voting from the start, which I think it's an interesting angle to think about it. I think they would form early. I don't think it seems like, yeah, all right.
Yeah, I guess the reference frame in L6 kind of has to form at the start, almost by definition.
Right. And then the question is, when does layers 2, 3 become unique to that? Just in the offsite, London, we came up with the idea that if you specified the unique ID, it would anchor the reference frame. And so now we're saying, once you anchor the reference frame, would you have the unique ID? It's not a bad assumption to start working with. So going back to Vivian's point, if we make that assumption, then you would be learning the associations right away.
Yeah.
You wouldn't be waiting for some future time to say, oh, now which seems right, by the way. It just seems like we're.
There are a few assumptions that go with that. I'll talk more about it in the next slide.
Well, but again, yeah, all right. But in shared learning, in some sense, you have to be doing it, right? Yeah. Okay. All right.
Okay. So I guess the question here is, if some sensors can only see different parts of the object, how can we build a complete model that we could vote on? I guess this is one of the questions that I've been thinking about, and I think we all have been also discussing this in one way or another. But if we have an eye that's looking at an object, and then we have a touch sensor that is inspecting the handle, and the eye cannot see the handle, and the handle cannot see the cup. The touch sensor cannot see the cup. Then what we want to build is a complete model. And how can this eye come up with an object ID that says, okay, this is a mug with a handle, or this is a mug with a broken handle, without even seeing what's happening here? There is a solution to this also with hierarchy. I'm
sorry, I don't understand the problem here. The problem is the eye doesn't see the handle?
The eye doesn't see the handle. You're inspecting a model, and you have two sensors, and you're looking at a cup from this side. But then,
right. So the eye doesn't see the handle. Why would you expect the vision system to have a model of a mug with a handle? I never saw the handle.
You're trying to build an object ID like a complete model.
Remember,
is the complete model
maybe a clear example is just that depending on our policy, we might not visit all the parts of the object. Like we talked, obviously each column is a small receptive field. I think one of the things we wanted to avoid is that every column has to go onto every location of the object. I think that's what you're saying, Ramy, right?
Yeah, if they don't see all of the locations on the object, if a sensor doesn't see, there is an assumption here that every column sees the full object.
Right, but remember, I'm talking about something different here. You've posed this in a way that the vision system doesn't see the handle, right? So the vision system, the finger doesn't see color either, right? And the eyes don't see temperature. So the models created by the visual system and the somatic system are not identical. So it's totally possible. I mean, this is a weird case, but it would be theoretically possible that the vision system doesn't form models. It doesn't know about the handle for some reason. And the tactile system does know about the handles. And so that can still vote. It's just like, because you still associate, the visual model with the somatosensory model. Those models are really, they don't have all the same features. They just like they don't, the finger doesn't feel the logo. So, and the eye doesn't see the handle. So it's possible that this system could still work like this. I mean, it's unusual that you wouldn't see the handle with your eyes, but if that was the case, the whole system doesn't fail. It's just that the visual system doesn't have different models for mugs of handles, and the somatic sensory system does. That's the way the system works. It's a subtle point.
I don't know if maybe an intuitive example would just be like, okay, imagine you have your retina is your eye is looking at this mug. You're moving over it. One column is kind of getting this input, and it sees that, and then another column is getting a slightly different input, and basically they each kind of follow a unique path. By the end of it, we're assuming they both have complete models of the mug. But if you were to actually just look at where they landed on the mug, it would be this very sparse sampling of all these locations. So it's not the fact that the handle is occluded, really, or like maybe that's an extreme example.
Okay. So that's what made this confusing. I think would be the better example in this case would be two fingers don't touch all parts of the mug.
Right.
So that's the better example. Or two retinal patches don't see all areas of the mug. The fact that you're talking about a broken handle, not broken handle, that's confusing things a bit. If Niels is right, you're really just saying perhaps you're just saying not everybody senses everything.
Yeah, I phrase it better here, but like this example is not the best. What I want to say is that we are trying to build a complete model of the object, and the sensors they don't see everything on the object.
Right. And so we've known this for a long time. In Monty, we assume that every visual column has experienced every part of every object, which is not really possible, right? So, which is what I think this is another way of expressing this here.
Right.
OJ, were you raising your hand? Or?
Yeah. I think I remember bringing some similar scenario a long time ago about two. But basically, the conclusion was that when we have two sensors like these, and we're trying to learn, because we can only pay attention to one, we can't really like learn from both things. Like, so I'm not sure.
Oh, that's right. You're right. We did say that.
Yeah.
Right.
I think that was in the context of different modalities, right? That was like
no. I think that's relevant in a single modality too. That's a really good point, because that's an important point. That tells you part of the solution. It's like we don't attend to multiple points at once when learning, right? We just don't do that. We have to attend to one, and so it's like we're building up a model one feature at a time, and yet we have to share that. Only during inference can we do this multi-sensor at the same time. Right? I mean, I forgot about that. That's an important point. I think that's what you're saying, Jose, right?
Yeah, that's right. Yeah, because I think I was saying that, and then you made that argument. And I was like, it's like touche. Okay, like, I concede.
Right. Even if I'm looking and touching at an object, I would attend to one location on the object, and it wouldn't be like I attend to one place where my finger is and visually, attend to another location. I might attend I might attend to one location. I might touch it and look at it at the same time, but you always attend to one location at a time. It's like learning, like building up a temporary model of the intersection. You can only there's a car here, there's a pram there, there's a bicycle here. It's one thing at a time.
I never really. I don't think I understand attention very well, because I don't know if when we say it's one thing, I don't know what level that one thing is. So
it's one. Yeah, go ahead.
I could be looking at this mug, and that one thing could be either, if it's at the lowest level, it could be a location on the mug, or if I'm trying to build a model of this mug, I could be attending have a volume attention around this mug and trying to build features. So my attention would be on the full mug, and then I'd be able to accumulate.
You could no, I don't think that's not the way it works. You can think of attention as you've narrowed down your area of interest to a single feature that you recognize. Okay, and then that feature is going to be in a larger reference frame. So if you attended to the entire mug, that means you've already learned the mug. And now you're saying, where's the mug relative to something else? So that's not what we're talking about. You might say, I'm learning the mug, and it's a unique shape. I've never seen it before. Maybe I've never seen a handle before. So then you're going to look at the details of that handle and look at the top, the back, and you're going to move around its edges and so on. If I see there's a logo in the mug and I already know the logo, then I could attend to the entire logo at once and say, there's this logo, and it's at some location. But it's always like attention is always a location, a subset location of the object you're learning, and it's always a feature that you can recognize at that location, whether it's a simple edge or if it's a more complex feature, it doesn't matter. But it's something you've inferred, a feature you recognize.
Right. Okay. It could happen. If it happens at a higher level, then I'm learning basically. I'm looking at the cup as a feature in a scene or something like that, and this would be my attention. This
right. You might say, where's the mug on the coffee table? So I see there's a mug, and then I say, where's its current pose relative to the coffee or the table? Right. This is important because thank you for bringing this up, Jose, because when we talk about shared learning, we want to be sharing one thing. It tells us that we're sharing one thing at a time. We're not trying to, we don't have multiple sensors at different locations. Everyone's trying to share what their learning is. It appears not like that. It appears like when learning, it's a slower process. It's a much more serial process. You're going to do like one feature at a time, and that could be shared. It's easier to share one thing to many people than many things to many people.
And that kind of matches with the conclusion we reached in London that it has to be a serial process. Whether it's like a fast replay or a fast switch of attention to different locations, that it has to be something kind of serial.
Right.
That said, I still want to hear about Ramy's proposal. Again, this is not in blood.
We're getting there slowly.
It might be a little different the way that I'm thinking or was thinking about this, but
that's okay. I still want a new idea incepted into my brain. All right. Yeah. Please go ahead.
I hope it's not too much noise. But, okay, I'm going to now talk about the learning of object IDs. This is another topic, and we just touched on it a little bit a while ago. Basically, during learning, features at locations are associated with a fixed random SDR in layer 2 and 3. This is how we currently think about this. Even like in the columns paper, it's like in the 2017 paper, we create a random SDR, we fix it, and then we say, okay, all of the features that we're going to see next, they're associated with this random SDR that we've put into layer 2 and 3. We do the same thing in Monty, except that the object IDs don't really have a representation, like a random SDR or anything. It's just like a string, a graph ID that we say, okay, this is object A, object B, or whatever. But we're still associating all of these features at locations only inside of this object ID. So what I'm going to argue is that ideally we want this object SDR to be formed over time through temporal pooling, where the object SDR itself is not fixed beforehand. So it is, rather than assigned, we want to learn it from the features at locations. And this is a topic that we may not all have consensus on, but this is how I'm thinking about object.
This is going back to SDRs having semantic meaning.
Yes.
Okay.
I'm not going to spend too much time in here, but I'm just saying that my thinking is that this object SDR evolves over time. It may start from some random seed, but it evolves over time and it becomes more and more unique as it receives more features. The reason I have this loop over here is because it uses its own context and then adds more and more onto it, and it just becomes more and more unique over time.
Well, so let's be clear. During inference, I agree with that. In some sense, during inference, if you have partial data for a column in biology, I think that it's likely forming a union of SDRs in layer 2, 3. And as you get more evidence, either from the single column or from voting, that SDR narrows down to a more sparser final result. So I think we can agree on the inference phase. You're proposing this happens during learning, which at first I'll hear your arguments, but it seems like problematic.
So the argument is that I want to say that this layer 2 and 3 representation is actually formed not just by looking at observations that are coming from layer 4 and layer 6 associations and its own context, but also embedded into it what the other layers are thinking about, like the hypothesis that's coming from the other layers. It basically builds these associations during learning and then uses the same connections for voting during inference. I think that I will talk about the problems or the implementation that I'm thinking about is to enforce some sort of sparsity in the representation here that makes the layer 2 and 3 representation really is more of a binding layer that just tries to come up with a representation to force agreement between all of these projections that are coming into this layer at the same time. And that would help with voting later on. I'll go into more details.
So I'm open to thinking about this, Ramy, but be really careful here. When you say forcing it, these connections that you've circled in red, we assume they're learned. And so it's hard. I don't know. It's hard to imagine how they force anything. That would imply there's some hard coding there or something,
No, I agree. These need to be learned. What would happen is similar to. I'll get to the spatial pooler in a second, but I'm thinking about this in terms of like a spatial pooler.
All right. Well, let's just keep going. Because we introduced a similar idea just a few weeks ago in London, where we talked about, hey, maybe the layer 2, 3 SDRs could force a column into a particular reference frame anchoring, even even if it hadn't learned it before. So we also introduced a similar idea. So, but it's not what we originally thought when we came up to layer 2, 3. All right, why don't we keep going then?
Okay. And yeah, I think, again, for the record, I think these are learned and these are refined over time based on the sparsity that's being that is being enforced in this layer.
Well, you did say they are forcing it into some form, so that suggests they're not learned.
It's a continuous refinement process. Once this is so basically the representation in the layer 2 and 3 becomes a better representation, and that will force these two here to be to learn to project to the right neurons, because these would be the active ones.
Okay. All right. Well, that's standard voting then. Okay.
Yeah, but once you have these, if these are formed already during learning, then voting is just reusing the same connections, because we already assumed that this is what the neighbors are saying, and it's continuously refined. Then voting is just using those same connections, and you wouldn't have to do anything extra.
Well, let's go on, because you say we can learn an object ID after the and using intercolumn or pooled representations. So that's suggesting that the circled arrows are training the middle column. They're learning. They're telling they're a learning signal for the middle column. That's what your sentence says.
Well, they're training. They're projecting first. This middle column,
and somehow they're training. They're training that one, which essentially somehow training has to occur between columns. The columns that are not exposed to something have to be trained. That's what shared learning is. So, but all right, I'll be quiet for a moment.
No, I don't know if it would be helpful just to clarify, and maybe we'll talk about this now, but like, if we assume what we were talking about earlier, that we just start with random IDs when we start to learn a new reference frame, and we associate those, like we learn lateral connections, I guess, is there a specific kind of computational advantage to kind of be aware of, or that you're proposing here? Because I don't know, when I think of like the pooling and like the SDR representation, that seems maybe useful like in a hierarchy, like if a learning module higher up is receiving this input or something like that. But it's not clear to me for voting why it's necessary.
The enforcing of sparsity?
No, the kind of why we can't just do the simple thing of, okay, each column has a random ID, a random SDR for each object, and then it just learns associative connections between those.
Yeah. So if we just do it if you just put a random SDR in here, we're making a few assumptions. One of the assumptions is that we're assuming that we know the object boundaries before learning the objects themselves. So it's like we know, basically, in a multi-object environment, we know when do we stop. Basically, the question is, when do we stop associating object A and start associating with object B?
But the random SDR doesn't say that. The random SDR just says that it just says I'm on some particular object. But you started off with a diagram which was about when you decide you're on a new object, right? There's no assumption in the random SDR about that. That just says we're on the same object, but there's an outer loop algorithm which you talked about earlier, which is like when do we decide we're on a different object.
And I mean, the assumption of it being the same object, isn't that more in the associative connections? And you wouldn't learn the associative connections if two columns are on different objects and they are not correlated?
Sorry, can you repeat that?
Like just the fact that there's a random SDR doesn't necessarily say, like, there are different SDRs whether it's the same object or a different object anyways. But the point where we're saying, okay, this should be the same object is the associative connection between two columns. But with the standard approach that Niels just mentioned, we wouldn't learn an associative connection if two columns aren't on the same object. Like their inputs, their layer 2-3 representation just wouldn't be correlated. So
Yeah, my thinking is that there's some type of supervision when you say, I'm going to learn a new object now. Let me get a new random SDR and put it here and then start associating features to this random SDR. There is a certain supervision because you're assuming that this random SDR does not adapt, does not change. It's an I don't know.
Yeah, I mean, I agree. Somehow there's like a kind of boundary saying we're on a new object, but it's a problem beyond the unique SDR. It goes down to the reference frame,
Right?
Because we need a new reference frame, and that's a harder one to get around unless we go and like start having like generic reference frames or something like that. Like, and so if we assume we have a unique reference frame, then it's quite easy to assume we have a unique SDR.
Okay.
Right.
Or that seems like a weaker kind of requirement.
I mean, to me, there's also the problem of it's a problem I didn't want to talk about, but just to me, the semantics of what the representation of the object ID is, that's just always in the back of my mind, and I just can't get rid of it. But if we start to send the layer 2 and 3 representation up the hierarchy, and they're all random SDR and they're all equally distant from each other, then we wouldn't be able to compare to.
Okay, yeah, so I agree. That was, I guess, my clarifying question is what is this specifically necessary for you? Is it necessary for voting, or is it more? It might help with some other things like hierarchy.
It's not required for hierarchy. It is the way I think you're talking about it. Imagine you have a whole bunch of columns in one region, and they're all inferring the same object. Now, in their layer 3 cells, they have different patterns, right? Because they're different cells. It's just different cells. And so now you have some number of cells in each column, but those cells are linked together. So when the pattern in column A is active, there's a different pattern in column B, but they're tied together, right? So now if you look at the output of layer 3 for all these columns, they are linked together, like they change together. And now if someone else, I could subsample from any of those columns, the cells in those columns, and I'll get the right answer. I don't know if that's clear. It's a subtle concept, but once you combine the layer 3 of, if all the layer 3s of a bunch of columns are tied together, then someone else up the hierarchy wants to know what they're seeing. They can just subsample from any of those columns and it'll work. They don't have to look at all the cells everywhere.
I guess I agree with what you're saying about subsampling. The point I was trying to make is if we have a mug with a handle and a mug without a handle, at a higher level, we want them to be more indistinguishable when we're building a scene, because what we care about at this higher level is how the arrangements. I just care about.
Why do you want them to be distinguished? Because when I put the mug on the table, I want to remember that's the mug with the handle versus it's not just a generic mug. It's a particular object I put on there. And
I think it could be useful to have both like a unique SDR and a semantically overlapping one. But this does feel like a different problem from voting and shared learning.
Yeah, right. I think when you're building compositional structure, you want the detailed thing. But I think we've talked about the challenge is learning new objects. Like you learn a mug and now you learn a mug with a handle. You don't want to start over from scratch. You don't want to start like, oh, I have a whole new thing I have to learn from beginning and end. We talked a lot about that, the hippocampus and the scratch pad memory and all this kind of stuff. So that's a separate problem.
But then we're assigning it a completely new random SDR.
No, we didn't. We haven't resolved that yet. What we ended up talking about is you have an object as we're learning. So what we've concluded recently is that as you're learning, you have sort of older fixed models in the cortex, and all learning first occurs in the hippocampal complex. Anytime you add a new feature, it's actually occurring first in the hippocampal complex, and it's building up a sort of a supplementary model to the, it's like, oh, I know mugs, but now here's a unique mug because it has several unique features in it. It's like, I know this intersection, but here today it has these features, these cars are in different locations. And so there's this idea between sort of more permanent fixed models and the new things you learn, which may or may not be fixed. And they're occurring sort of in parallel. We haven't resolved all the issues with this yet, but we do know, at least I think we can be certain that that's happening. We're not adding these features immediately to the cortical model. We're adding them in a sort of supplementary model space in the hippocampus. So because all new learning occurs there, we kind of reach that conclusion. It at least occurs there quickly. So there's a whole bunch of stuff going on underneath these basic ideas we're talking about here. Yeah. I wish it was all clear, but it's not. But we just have to keep all the balls in the air at once.
Yeah, I think in Monty, what we currently do is that we send up the object ID as just the string, and we say, okay, it just has to be exactly the same.
Well, I think that's okay. I mean, for Monty, what it's doing today, I don't see a problem with that. But it's not. But we need to extend it. If you were going to talk about shared learning, one could just say here is a two columns. One is learning a model, and one is currently not on that model. It's not sensing anything. It's out of the picture. It's sitting on the side. And what I want to do somehow is to take the column that's learning something and transfer some knowledge to the one that's not learning something, so that it is learning something, even though it's not sensing it directly. That's the gist of this problem. You could just express it with two columns. One's getting input and learning, and the other one's not getting input, but we want it to learn what the first one's learning.
Yeah, or just they're sensing different parts of the object. And
well, that's interesting. I don't think so. We'd have to some figures or drawings would be very helpful if I could do this on the whiteboard, but I'm not going to try today on next Calidra. In some sense, when we learn something new, we're always attending to one feature at a time. That feature could be big, like a logo, or it could be very small, like an edge, but it's always one feature at a time. And so essentially all the columns they're getting input are all inferring the same thing. And that thing is now going to be a child of some larger object. And so to say that there's a column that's on something else, well, imagine like we're learning they may be getting input. We're not attending to that input. Therefore, they don't count. They're not voting. If I'm attending to the logo, in V1, if V1 is attending to the logo, let's say then the other columns in V1 are not participating. Even if they're getting input, they're not participating. They're sort of silenced at this point in time. And Hoji's got her hand up.
Oh, sorry.
No, sorry, that's the point.
Yeah, I think as I'm just throwing my kind of desired thing that could happen. I'm not sure about SCRs at the object level sharing like some semantic. I forget the wording that you used.
Semantic meaning.
Yes, sharing some
like
semantic
you can look
meaning.
at the bits. By looking at the bits, you could say something about what the object is.
Right. So I'm not sure about at the object level whether that's required, or I feel like that's very constraining. Even though I understand that we don't want to necessarily I get the feeling like a mug with a handle and mug without a handle. It feels like it should have similar object IDs, SCRs, but I think it's not at the object level, but at the feature level, maybe they share SCRs.
Well, they do, right? I mean, because their compositional models have similar features at similar locations.
Right.
It's just that one location you have something very unique, and on from the other one.
Yeah, but it's not at the layer 3.
This goes back to the question of classes of objects, and I also like. This is unresolved. I guess
one kind of workaround or thing that will help that we've discussed more recently is just how, having multiple models in many different columns helps with this a lot. In that, if you have a column that kind of recognizes whether that mug, whether it has a handle or not, and that's learned in a hierarchy. That's your kind of general version. But then you can have another column that's recognizing the specific version of the handleless mug, and both of those can be communicating their IDs up the hierarchy. So that is an alternative solution that
Right.
I don't think it has any major issues. It just means that we have many columns. I think what we can all agree is that functionally, in a higher level, I think we can agree that functionally in a higher level kind of reference frame, sometimes it's important that the child object is very specific, and sometimes it's important that it's kind of more invariant to these details. And so somehow that spectrum needs to be captured, and the question is kind of how you encode that. But
the way I see it is that in the higher level, it always needs to be indistinguishable. If I need to figure out more details about this object, I'll just go to the lower level. I just traverse.
But you have to be able to make predictions, right? If I put
not at the higher level.
No, the higher level, but right, but the higher level has to be able to tell the lower level, yes, you should be seeing this, or no, you shouldn't be seeing this.
It's seeing an abstract model of, like, it's just says this is a mug. I know it's a mug. I don't remember exactly what kind of a mug, but I know that there was a mug over here in this scene. If I wanted to, I could go a level deeper and then start thinking, okay, this one had a handle, this one had a broken handle.
But it depends on what object you're recognizing at the higher level. So, like, say a generic dinner table scene, that's composed of these generic models. But like in Copenhagen, every Christmas they have this thing where they invite artists to make a very specific, like a Christmas table, basically. And it's always inspired by their life, and they're always quite interesting. But those are like very specific instances of a dinner set, and you can recognize that as a separate thing. And so in that case, the child objects are very specific.
Yeah, but the different object at the higher level is just the different scene or the different theme is a different object. So you're making that distinction at the higher level, and then you're saying, okay, I think that there was a cup themed with Christmas stuff at this location. If I wanted more details about this cup, I would just have to revisit the lower level because I can't store all the details and
you wouldn't store all the details.
The high level stores the specific object ID, and because you see the specific Christmas mug, you know you're on this artist's dinner plate setting. It doesn't just store mug, and then you recognize mug. This could be any dinner setting.
Can I try to maybe bump this up a level here? There's a series of problems we haven't resolved. Classes of objects is one of them. Forking of objects, like I've learned an object, now I'm going to create a new one that's just has some new features, but it's now a unique object. I know that object is unique from the previous ones. Like I have the cracked cup mug versus the uncracked mug. There's a series of problems like this we haven't resolved, including shared learning and so on. They're very mysterious. The answer is puzzling, right? Now, in my world, this is just my world, I don't see tweaking these SDRs to have meaning as a solution. My understanding of SDRs is that they're not going to have that. And somehow there has to be another solution. And so one of the things, so we've talked about some things. Some of the progress we made a couple of weeks ago in London was to realize that there's these parallel sort of models of the same thing, the hippocampal model, which is sort of the differences, and the cortical model, which are sort of the permanence. And we didn't resolve all the issues with that, but at least it's a different approach to saying, how do I form different classes? How do I learn new things without having to learn everything? And so, that's one direction to go in, which I think is very promising. The general direction of sort of saying, we're going to pass up some sort of, like the general direction of using SDRs in the ID. The reason I don't like that is because SDRs, by their very nature, if you make them sparse, they don't have the ability to represent semantics. They have to have more bits active to represent semantics. And so I told you many times, I used to believe this, but now after I got into it more, I ain't going to work. So so I'm still in that category, and I could be wrong, Ramy. I'm open that. I'm open to that.
I agree with you that layer 2 and 3, they need to be very different. I think I brought this up before. Maybe let me.
But Ray, we have a definition of layer 2-3 right now, which is these are unique to particular objects, and that may be wrong, but that's how the whole thing is working. So if we want to start moving away from that, it gets difficult for me. I don't know how to do that yet. We also at one point talked about layer 2 and layer 3 are different cell types, the different cell populations. So one could be more of a class of objects, and one could be specific objects. I'm open to that too. That's not a bad idea. But those would be two different representations, and they would be handled separately.
Okay, I just don't want to go off track here, but this was one thing that I mentioned before with the I agree that the layer 2 and 3 representation of the object at this level, this is a region 1 level, it needs to be sparse. It needs to be different, and it could be random. It's morphologically dissimilar. They're just different features. But the way that they project into layer 4, I think that this layer 4 representation, when it gets learned of this projection, they will have some semantic meanings that just make them.
But where is it going to come from? I mean, if they're unique SDRs in layer 2-3 and layer 2-3 projects to layer 4, where's the semantic value being added?
It's added from the higher level scene. I can talk about that later. This is
sure. So the projection isn't. Then you're saying that arrow going from left to right doesn't have semantic meaning, but you can provide in context. I form unique representations in the right column in context, right. and now they do have semantic meaning, but it's not the line itself. The SDR being passed left to right doesn't have that. You put them in context, and even if it's projecting into layer 4, once it's entered to layer 4, what I do with it is an open question. But in that case, we form SDRs in layer 4 in the right column that have more meaning than the SDRs on the left.
Yeah. So,
but that's because we're using the temporal memory algorithm. It's not because the SDR coming from left has changed or anything.
The end product here is that the SDR that is here for a banana and for an apple, they are sort of very close. They're overlapping. They have some semantic meanings because they're interchangeable in the fruit.
Let me step that back. Once you've entered layer 4, Ramy, there is no SDR for banana and there's no SDR for apple. The SDR that's formed in layer 4 is in the context of the fruit bowl or whatever you want to do it. It's a different SDR. It's not you.
You mean the mini columns that are active? Ramy?
Well, you pick a different. Yeah, you're using a mechanism to make a different set of cells active, and that different set of cells is no longer banana or apple. That different. It's now. You could think of. It's not even that. It's something in the context of it's banana in the context of some larger object and location on the object. So it could be now it's the banana on the right of the fruit bowl. I mean, I don't know. It's challenging because your fruit bowl is not a very good object. It's not a specific object to do. It's sort of it's like an intersection. So it would be happening in the hippocampus. Unless I have that fruit bowl every day made out of plastic fruit, I won't learn that particular arrangement.
Okay, I have a lot of thoughts about this, but I don't want to. Jose, do you have a question?
I was going to say, I guess, I don't know. It's good. So the reason why I don't think the SDRs at the banana and the apple and L4 should be similar is that like fruit is a conceptual category, not arising from perceptual similarity. Like if we share it's not like. Yeah, that's why I don't think that's all I wanted to say.
I think Ramy has proposed a mechanism how you can use top-down feedback to
force it to be
have
similar.
Semantic overlap. But maybe it's better, Ramy, to say that for another day, and then that way you can get to the stuff about voting.
Where were we? I think we. Okay, so this is where we were. So the the high level idea, I'm not talking about the mechanism yet, but the high level idea here is that, again, we would just, whatever we form here is going to be, it will have some embedded information of what the neighboring columns are seeing. And just as a side note here, whatever this representation, well, two things. This representation here is also formed by the neighboring columns. So they're all just being informed by neighboring columns at the same time. So this is also whatever is being learned here. It's learning by forming a representation that comes up with a representation that forms agreement between the neighboring columns and what it's also seeing. But it's also helping build the representations of the neighboring columns because it's just bidirectional association. And the general mechanism would be to force sparsity here with something similar to spatial Pooler. But I'll get to that next. And also the other thing is that there is some embedding of location in here. So I still haven't worked out details about this, but maybe up for discussion. Because I think that the representation that is being formed, and as long as this one, the object ID over here keeps getting adapted and keeps getting changed, it is basically it's also embedding information about the location of the observation that's being seen. The sensor module provides 3D or depth information and location in the reference frame of the object, and that is helping these object IDs build context around.
But is that going to constantly be changing, or is that stable across all locations on an object?
That's the point. They are changing, and there is a mechanism that forces this here to over time become more stable as we see different parts of the as we move over the object. It starts very unstable, and over time, because it averages and learns to force agreement between these representations here, it becomes more and more stable, and it learns object IDs. I don't have any proof that this works, and I can't run simulations, but that's my intuition.
But, yeah, in terms of kind of voting and shared spatial information, is it fair then say kind of like a key part of the proposal here is that like you're kind of you're learning an association essentially between specific locations in one reference frame and specific locations in another reference frame?
Locations and features. So whatever comes up here in the object ID, this is the hypothesized object ID. But that when building this object ID, you're building it from features and locations. It's not a random SDR. It's
right, but I guess in order to not be bag of features, because as soon as if it was totally stable, let's say like even though that SDR is informed by I guess whatever locations on the mug we explore, once it's totally stable, that SDR now represents mug, and that's going to be associated with the other SDRs that represent mug, and so as long as each column is just getting the local feature associated with mug, then when they vote, it's going to be bag of features.
It's not because there's a specific arrangement of these columns. So these are coming from specific synapses. It knows that if I'm looking at the phobia column, it knows that the information that's coming, it's wired on completely different channel, different synapses than the one that's coming up from a different column. So in that way, the column is able to if the information is coming from a different channel or like a different column, it wouldn't be the same. It can't form. It's not a bag of features because it's a different channel, different synapses.
Yeah, so it's kind of trying to encode, I guess, relative locations
through the arrangements of the columns. Yes.
Okay.
But the locations themselves, the depth that comes with it, that is kind of informed by. It is encoded in when we're building these object IDs. That it's not enough that at this neighboring column would be seeing this feature. It also knows more about that this feature will be relatively shallower or deeper in terms of like distance. I just have an intuition for it, but I don't know how to explain it. It's very difficult to put into slides.
I mean, I think it's a good point that during voting, the receiving column can make some inference on the shape of the object based on which columns it receives the object ID from, the same object ID from. I don't see it where the dynamic SDR comes in that picture, but I think that's an interesting idea to think about, that depending on which columns are on the object, the receiving column will get votes off that object ID from arriving at different synapses. So I don't know, I haven't thought through yet if that would be useful.
No, I don't know how that would work, but
yeah, there are open questions about also rotation.
Right.
So have we got to the
scale and stuff?
Have we got to the gist of your presentation, Ramy? Is there more? Have we gotten to the main points yet? Is this it?
From a high level, not mechanistically. I was going to talk more about spatial poolers and generalizing that mechanism to work between layers, and how we would basically, like, more details about how we would perform the object ID here. But it's you get the gist of it now by saying that, I'm trying to enforce. It's the same mechanism of spatial pooler, except that this now here is getting inputs from multiple locations, multiple layers, and it's still trying to enforce sparsity. But because it's getting inputs from multiple layers, you're really trying to come up with a representation that forces agreement between these. Comes up with this SDR that is that is binding. This is the best.
Well, it might. I'm not following everything you're presenting. So, but what the spatial pooler does in its current form. If we're going to talk about spatial pooler, we have to use it in its current form. It takes some complex representation of varying sparsity, right? And what it does is it turns it into not really an SDR, because it turns it into mini column activations. And mini column activations are not terribly sparse. They're like if I have 1,500 mini columns, or there might be 100 active or something like that, or it's not super sparse. Not as sparse as when we refer to an SDR, that's like a 2% sparsity. These might be like 10% sparsity, something like that. And it's an activation of mini columns. And those mini columns, actually, you could assign somehow meaning to them, because they represent some sort of common feature in the input. But anyway, so what I was getting at is we think about the spatial pooler initially for how it would form representations in layer 4. We think of the mini columns sort of representing point normals or edges, or some sort of oriented feature. And then of course, that plays into the whole mini column mechanism, which then represents that feature in a unique context. So these are a lot of words, but these are all in those early papers. So the idea that you might have mini columns in layer 2 and 3 that are being driven by a spatial pooler, independent of the one that's driving layer 4, is possible. And it's not a bad idea to think about that. So you want to think about it, but I want to be clear that it's not the same. The spatial pooler does not result in an SDR. The spatial pooler results in a not so sparse or moderately sparse representation. It doesn't have the output of it. The active mini columns. What's that? What would N stand for?
Moderately.
Oh, MDR, moderately. Yeah, right.
Or moderately sparse MSDR.
The thing about it, when you have that level of sparsity, like the mini column sparsity, it's not very good for much. It doesn't have all the properties we like about STRs. They can easily be confused. You can't form unions of them. It's not a good representation, and that's in our theory in the biology. These would be initiated by these double bouquet cells, and they don't project anywhere else, right? They're just local. So you really want to get into the sparse form before you send it to someplace, because that's where you can do some good associative memory with them.
Yeah.
So the idea that you might be doing a spatial pooler in layer 2-3 is good, but if you're going to call it a spatial pooler, don't get an SDR out of it. You're going to get mini columns. And then you're going to have to figure out how you're going to pick within that context, some context, get an actual SDR. So the spatial pooler always goes with the temporal memory. You can't really separate those two out.
So
that makes sense.
There are some, this makes sense. And the spatial pooler in its current form, it sends to the double bouquet cells, which are not really SDRs. They're SDRs once once they figure out what the activations are in the mini columns themselves.
Right.
What I know that the spatial pooler is designed for this, but I was thinking there are some concepts from the spatial pooler that we could borrow, where the target layer doesn't have to form mini columns, but it could just be like an SDR to SDR as long as they're enforcing.
Well, okay, so fine. So that would be that's some sense the assumption we have already for layer 2-3. We assume that there's these inhibitory cells. They're everywhere. They're everywhere. That force sparsity, right? Enforce sparsity. They enforce the sparsity in the cells in the mini columns. They would enforce the sparsity in layers 2 and 3. I guess you could say, what the spatial pooler basically picks is n winner take all type of thing, and you can make the n very small, then you'd get sparser representation. But then I wouldn't call it a spatial pooler. I call it something else. Just call it we have a sparsification mechanism.
Yes.
Otherwise, it's going to be really confusing to call it the spatial pooler.
Yeah, I completely agree. I only wanted to visit the spatial pooler as something that we know already works for taking some input in some sparsity level and then like some density, and then projecting it to another layer and using local inhibition or global inhibition to form some representation, maintaining the sparsity. And I was just going to go from there and generalizing the spatial pooler into something else.
All right.
But yeah.
Can I ask a high-level question before you get into the mechanism stuff here?
Mm-hmm.
Just in terms of what you proposed today. So kind of to summarize, I feel like there was kind of two problems you wanted to kind of help with addressing. One was sort of the sharing spatial information for voting, so we're not doing bag of features. And you kind of described, as you said, kind of like an intuition for maybe what's happening and some ideas there. But as you said, kind of, still some kind of details to clarify. But then in terms of shared learning, I just wanted to check my understanding, kind of what you showed on the previous slide of the this one. I guess where that came in. So because there's no kind of transfer of knowledge, I guess, from one column to the other, but is the idea that you avoid needing to do that in the first place, or
it depends what you mean by transfer, because when we form an object ID here and it's taken into consideration, it's formed by just looking at the neighboring columns and its information over time. I would think that this is it's not transfer, but it's representing the object ID in terms of features around it and from neighboring columns and from its own. So it's more binding than transfer, but I don't know if this word has any meaning that makes sense to you.
Yeah, I guess I'm just thinking, like, with the opening problem we were talking about of like any given sensor won't, like, your finger won't touch every location on the mug. It feels like the idea is that you're avoiding that being an issue because it's going to get so much information from neighboring columns that even if it visits a location it hasn't been to before, neighboring columns will visit locations they've been to before, and between them they'll...
But wouldn't it still have a lot of issues if it suddenly sees totally different points on the object that it hasn't visited before? Like, we still have the normal matching mechanism going on.
Yeah, that's why this is adapting and it's learning. So as you are moving like this, if you start to sample like a completely different location it hasn't seen before, the object ID needs to learn, needs to adapt and to learn, because it will have issues, because neither what it's seeing now or the the neighboring columns, these are locations that may not have been seen before.
But wouldn't that then make the problem actually worse instead of better? Like we just have more instability in the system, and it still needs to see all of the locations before it stabilizes and can do inference?
I don't know if it's worse. I think it's inevitable. It has to learn this kind of translation invariance in the object ID. I mean, this is the best I could come up with in terms of what I think the best solution is for voting and shared learning. It's unstable until it learns a stable object ID.
So then, is it correct to say that this solution does require every column to visit most of the locations? Because it wouldn't stabilize before that?
I am not sure. I don't have a good answer to this. I think at some level, this is totally speculative, but at some level there are shared features that it can learn. Like there is, my answer is not going to make sense, but yeah. So
I'm going to say this again. I think we're talking about a problem of how, not every column can experience everything at the same time, and therefore we have a problem. And so we need to have some kind of shared learning. But I think this image here is, in some sense, posing the problem very differently than I think it should be posed. This is posing, you have multiple columns observing object, and how do they help each other? Because they're observing different points on the object and so on. I've come to believe that the general solution is very different than this. The way you think about shared learning is to say there is one feature detected at a time. That feature can involve multiple columns, but they're all detecting the same feature. It's something I previously learned, or if it's coming from the retina, it's just a basic feature from the retina. But there's one feature at a time, and we're going to attend to that one feature at a time, and we want a whole bunch of columns to now saying, oh, we're all going to learn this one feature at some location. Now we're all going to learn this feature at some location. Now we're going to all learn one feature location. It's a very different phrasing of the problem than here, where we have multiple columns detecting different parts of the object, detecting different features in the object, and sometimes vote the coordinating. This coordination occurs during voting, during the inference. But I think this is not, I believe, what's happening during learning. I don't think this image here, which is very nice and cute, I like it. I think it's missing the essence of how I'm proposing that the general solution is very different. It's to think about it less on a column by column basis, just thinking like, okay, the system recognizes a feature that can involve one or many columns. And now we have to say that feature is at some location to some parent object. And how do we share that knowledge across lots of columns at the same time? This is a different phrasing of the problem here. I think that's how, if I'm interpreting this correctly, I think that's what's going on here. Does that make sense? I mean, I'm not saying I'm right. I'm just saying that's the way I've been viewing it differently lately.
Right. Yeah, I think that, at least from my understanding, that's a fair way of.
Right. Yeah. And since it was so hard to come up with the solution, the direction we came up with, I feel like it's probably right. I feel like it'd be hard for me to go back from that, but I'm still open to the idea of, I'm interested in spatial pooling in layer 2 or 3. I like that idea, actually. So I don't want to explore that, but I just think that some of the details we're talking about here is on the assumption that we have these different columns. It's just sort of like with the picture here. So like I have two straws and they're moving around together on the object. And if those two straws can't recognize something together, I don't think they're both learning independently. You know what I'm saying? I don't think I can attend to one of those two straws. It seems like I'd have to tend to one of the straws or the other straws. And that was enough straws that I could recognize the underlying feature. But I can't learn two features at the same time on the object.
Yeah. I want to say I have some complex thoughts that I'm not sure I can convey them. very well. But I think that there are some shared things that we can learn from saccading the same ways on different objects, like translation invariance, rotation invariance, and maybe scale or things like that. And these are things that we can learn and we can apply to different objects.
Right, but what does that have to do with
like a scan path kind of thing, or
what's that? Sorry,
you mean like a scan path? That's kind of like the term for, like in the 70s, there was theories that we would kind of follow stereotyped sequences when looking at a face or whatever, but actually the evidence isn't very good for it. But
yeah, not a scanned path, but if it's the same way when I'm looking at a cup and I rotate my sensors, my whole agent rotates, and then I look at another object and my whole agent rotates. There are some shared learning that happens there. There's something that I can get from this kind of information that helps me also apply this same rotation invariance to other objects and expect to see what I will see when I rotate.
Ramy, those all make sense, but I don't know how does that have to do with this mechanism in the shared learning we're talking about here? I'm confused. It's like that came out of left field for me.
This is the problem that Vivian was talking about how having to see all of the features for everything. But
now you're talking about rotation invariance and scale invariance. That's a very different problem. So, well, at least right. That's not what Vivian was talking about, right? So, I mean, not that those aren't problems, but I don't. They weren't mentioned yet today. So all of a sudden they're here and now. I don't know why.
Yeah, like I said, I don't. I'm not going to be able to connect these very well. But yeah,
the general way I would approach a problem like this is you write down all the things we're trying to solve. Like, okay, you screwed in scale invariance. Well, we haven't been talking about that at all today, but that's a problem, right? So, so we can write down all the things we're trying to solve it, and then ideally you would come up with a solution and then we have things we've learned. Like I've learned that new knowledge is first formed in the hippocampus. I'm stuck on that now. I'm not going to move away from that. And so we could have these partial solutions we have, and then we try to come up with an overall thing. I felt a little bit like when you introduce scale invariance right now, it's like, oh my God, we haven't been talking about that. So are we trying to solve that too? So now I'm confused. I don't know how that relates to this. So it's not a bad problem. It's something we have to solve, but it's like, okay, you didn't ask me to think about that yet today. So now, like, I don't know where to put that.
Yeah, disregard this statement. It's
okay, right. So, but you're using it as sort of a justification for this basic idea that these multiple columns moving around, they're learning independently, but they somehow have to influence each other. And I personally have moved away from that. I've moved away from no, they're not doing this. We only learn one feature at a time, whether it's a simple feature or a complex feature, one feature at a time during learning, and that is not reflected in this image. So we could pick apart the idea that we're learning one feature at a time and see if that's wrong. But the premise I think you have here is that you're multiple columns learning at the same time. They're looking at different features. They don't know they're on this. They have to coordinate somehow. But I think that's in my mind, I've moved away from that. That's not what's going on anymore. We don't do this.
I also don't know how this fits well with the attention problem that Jose and you brought up, because if you're attending here and you're trying to learn an object ID here based on the features, what I'm proposing is basically that all of these columns are learning together at the same time.
Well, what they are if what they're trying to learn is there is a feature at some location on an object, we want a whole bunch of columns to learn that. If you're trying to say, I have a bunch of columns learning, each one is learning something different, and simultaneously I'm trying to share that information, which is where I would have originally started from. I don't think that's true anymore. I think we don't, we're not doing that.
Maybe just one way to kind of summarize or compare whatever, at least my takeaway is this isn't, or at least you haven't described, maybe you have some intuitions, but this isn't a solution for the shared learning problem. shared learning could be resolved through kind of what you're saying, Jeff. Like you attend to one thing and then all columns are learning about that. What you're describing here, Ramy, could maybe still be useful for voting amongst columns that have a fixed spatial offset. Because like when we, at the very start, in terms of the open problems, I was pointing out that like what we described in London, where we kind of have 5 locations that get shared kind of to all the columns and we sequentially attend to, that seems powerful, but that's 5 locations. Obviously, there's thousands of columns. And so maybe it's complemented. We talked about that, maybe it's complemented by some other mechanism which, locally associated columns vote together, again, without doing bag of features. So
interesting.
Like in terms of kind of, if you were to kind of develop this idea further, I think it would be interesting to understand a bit more how it might address that problem, and maybe in the context of like Monty, for example. Like, okay, in Monty we have access to the locations, we have them represented in explicit Cartesian coordinates. How might we share that information to kind of do this local non-bag of features voting? And then the question is, okay, how well does that work, or is it vulnerable to things like rotation or scale? Because it's in some sense, I think there's a risk that it's kind of a model-free form of spatial alignment, because you're relying on this fixed offsets. As soon as an object starts rotating or changing in scale, then what each column is seeing is going to be different.
Yeah, I have ideas about rotation and scale, but I'm not going to get into that because I just didn't prepare to.
Yeah, no, and I appreciate you putting this together today at short notice. I think
it's good conversation to have, even if we bang our heads together.
Yeah, and I think Jeff, I guess you went there on Monday, but part of our motivation was just in the lead up to the brainstorming this next week is just to kind of put our heads, kind of pull them out of the potential local minima that we were in, and just think like, okay, what is the solution space, and then if that gives us greater conviction that the sequential shared learning is really important, then maybe that's a useful thing. And I think there was a lot of interesting discussion.
Right. And also really, what are the questions, if it's talking about next week, what are the things we really want to understand? If we want to understand shared learning, that is important, but that's not quite the same as, the scale and variance and things like that. Those are not necessarily the same problem. They might interact with each other. So I'm not sure exactly what we want to accomplish, but it'd be nice to define a clearer problem, a very clear problem of what we want to talk about, and then that would be helpful for me.
Yeah.
Right.
Sure.
Yeah. I don't know if you had gone any further on this idea of mini columns in layer 2-3, but I have two. Ramy, when we first came up with the idea of a random SDR in layer 2-3, I didn't like it, and I still don't like it. It was like random works, but generally brains don't work on random processes, and it at the moment it fit all we needed to do. Now we came up with this idea perhaps that the SDRs up there are not purely random in the sense that they're tied to anchoring in reference frames. And so if I anchor my reference frames, it would determine the SDR on layer 2-3. And if I know the SDR on layer 2-3, it would anchor the reference frame. That's an idea that we don't have a lot of evidence for, but it theoretically it was nice. And so, we can explore that one. I'm just pointing out that to say that I could agree that I don't like the random choice of SDRs in layer 2-3 doesn't mean that they have semantic meaning. It just means that there could be mechanistically tied to other things. And so one thing they could be, as you suggest, maybe somehow semantically derived, but I've never seen a good it hasn't worked for me yet. And but they could be mechanistically tied to other things. So that, like we discussed, specifying an SDR could dictate the anchoring. But I don't know how that works. So,
Yeah, me neither. I just
So, is there anything else on the spatial pooler in the layer 2-3 that you want to talk about?
Yeah, but I could do it some other time.
Well, I don't know. I'm just curious. I'd like to. Can you just give like
Let me go through
the
the
1 minute
slides.
summary? What's the 1 minute summary as opposed to the detail?
So I was going to go through the spatial pooler just to describe how we're doing, global inhibition and all of that,
Right.
and forcing sparsity and why this is useful. Some other studies like from Olshausen and Field that, like
Right.
coding and things like that, that also force sparsity and find some really nice, interesting properties.
Right.
But also I was going to just review some neuroscience or neuroanatomy about the projections, excitatory to excitatory between all of the layers. I wanted to first just show well, maybe I could skip over this. This is not really.
No, that's a good. I don't know. It's a good diagram.
Yeah. Are there some that maybe we don't often account for?
Well, first of all, this is so these are the proportions of excitatory connections to excitatory to excitatory neurons, and some of the things to just note here is that the thalamic input is extremely small, actually, to a column. So
that's numerically
right.
That is not their impact. That's just number wise, right? So what that tells you that is not an SDR. What that tells you is it's a driving input that's not particularly sparse, because as soon as you get an SDR, it's always going to be a large numerical connection, even though the influence might be very small. So this basically, it's somewhere between 5 and 7% of the synapses on layer 4 are from the retina. But that can be very misleading in terms of their impact. They're still one of the driving forces there. They're important.
Right. The driving is just in terms of quantity. Like there's less synapses than what we see going from all these other layers between all other layers.
Right. So you have to be really careful about the thickness of these lines. It's very misleading at times.
Yeah.
But anyway, it's.
Every layer here receives some input from every other layer. Yes, there is more dominating inputs or projections between some of the layers. But if you just look here, it's like all of them just receive inputs from all the other layers. I think
layer 1.
Well, layer 1 has, I think, mostly interneurons. That's not covered by this figure because this is.
No. But the problem there is like layer 1 has all these apical synapses from layer 2, 3, and layer 5, and those aren't shown here at all, right? It's very misleading. These are useful diagrams. They can be extremely misleading.
This is only excitatory to excitatory. So there are 3 others that are going like the whole other combinations like excitatory to inhibitory, inhibitory to inhibitory.
But when they talk about layer 1, they're just talking about the cells in layer 1. I don't know.
I'll share the paper.
But I've seen this paper. I'm just pointing out you have to really put on your interpretive hat when you look at this diagram or things like it. Right. So what was your point about this? What was it? You brought this up because of the recurrent connections, layer 2, 3, and layer 4?
There are recurrent connections over here. There's a lot of recurrent connections, and in another paper they hypothesize about this being, or they just say that there is a tight positive feedback loop in here, which I think is good evidence that. So what I mean by a tight positive feedback loop is that when a cell projects another cell, that other cell projects back to the source neuron in a tight positive feedback loop, which is basically saying this is stabilized. It forms a network mesh that stays stable and stays active. It's more likely to happen here in layer 2 and 3, which is a good thing, I guess. A lot of our theory depends on it. And then I was going to go into generalized pooler, and I was going to talk about how I think that this could be generalized into like happening everywhere. every layer basically just forms its own representation by forming its representation that makes the projections agree here.
But you're saying every layer has the same mini column architecture, so it's spatial pooler plus temporal pooler, right?
No, I started from here. I know I have it as a. Let's see, can you see this? This is more of what I mean, but I wanted to keep the same figure of spatial pooler. But I think that it could be just an SDR, and if two layers with two SDRs are just projecting to a layer that has an SDR, it's still forcing the same sparsity and forcing having those nice properties of clustering and maintaining overlap and all of that nice things about the spatial pooler.
What I have, okay, all right. I'm not sure where you're going with this. So, a single learner was used to learn represent all layers for the goal of maintaining sparsity.
Let's see.
Right. I mean, the sparsity is just something that's enforced locally. And so, but something has to tell, you have to choose which cells be active or not. If you don't choose which cells be active, it's just a random SDR. But if it is choosing which cells be active, you have to have some sort of forcing mechanism. That was the mini column, bouquet cells.
Or is this kind of where it's more like an iterative, like there'll be some random connectivity to begin with, but those synapses aren't going to be particularly strong. And then, so if you activate the SDR in the top and the bottom, they will by chance activate a subset of cells in the middle. But then I think you can kind of iteratively run this, and as those synaptic values change through competition, you will have some that are strengthened and some that weaken. So if you want to call that kind of forcing, it's not really. It's maybe more like convergence.
It's more like a random start. I mean, by random,
it's a random start, but it converges to something that is kind of shared by both of these layers.
Well, I don't think it's shared, but it's
informed by both of them.
We're talking about 3 layers of cells here. Is that right? There's a upper layer, right? And so the middle layer is essentially you can just say it's going to form it's always going to form an SDR, whatever reason, randomness of connections, it doesn't matter. It's just going to settle on an SDR because it wants to, and the cells want to be active and they're going to inhibit each other. So you're going to get an SDR. And then when you get an SDR, then you can associate it with other SDRs. And as soon as you associate it and form synapses, then they'll reliably invoke each other. It's associative memory, right? So that's totally correct. I don't know what you're going to do with that at the moment, but
so what I'm saying here is that this could be a layer 2 or 3 in one column, so these are 3 layers of object IDs in 3 different columns, and what's happening is that they're training this one in the middle.
But say training it is a little weird. It's like it's just saying like they're going to make an associative connection with the one in the middle. The one in the middle, I don't know how they could. It's going to be random. You haven't given me a reason why it wouldn't be random from start. That pattern in the middle one is going to be just by chance what initial connections you had. Otherwise, how else could it work?
No, it's random. It starts random.
Right. So as soon as you pick a random SDR there, then the 2 other ones will associate with it, and that's it. It's done. That's our voting mechanism, right? You have an SDRs, and they could all be randomly chosen. The 3 SDRs could be randomly chosen, but as soon as they exist, they're going to start at the same time. Then you start forming connections, and they'll be voting. They'll be associatively linked. So I don't know how you call it training, but it's more of just associative memory.
Except that associative memory is between two layers. This one here.
Associative memory is between 2 SDRs or multiple SDRs.
Right.
It doesn't have to be layers. It could just be just SDRs anywhere.
I don't know if it's helpful to break it down. Like, obviously, if you had forget about the very top one right now. So you just have the input from the bottom. That's going to randomly activate a subset of cells, as you say. So that's a random SDR. Now, separate from that, now imagine we activate the top one. That's going to activate a random set of cells in the middle. Now,
But wait a second.
Now we say both are active, but we constrain the sparsity. There's a subset of cells that are going to win between those two sets of random inputs from the top and the bottom.
Yeah, but that
so
random
that's
set
going to be unique to this kind of input or whatever.
Right,
or like,
but that's going to be too sparse. Imagine we have 2% sparsity coming from the bottom to the middle, and we have 2% sparsity from top to the middle. Let's say they're all 5,000 cells each. So you have 100 cells chosen out of 5,000 from one direction, 100 cells chosen out of 5,000 the other direction. There'll be almost no overlap.
There doesn't need to be overlap. It's just.
But then you can't move together. There's no common ones. There's no common. That's the point.
I guess. So you need some overlap in order for the bottom.
Right, but there won't be.
Say the cells that are active from the top. So those are the ones we now want to. So now say we want 50% of those that were randomly activated by the top. We now want to learn to associate those with the bottom ones.
Right. Well, you start off by saying the top down is going to evoke one set, and the bottom up is going to evoke another set. Those overlaps of those two sets will be nothing or so small, insignificant.
But so there's the overlap in able to drive activity, and then there's the overlap in terms of where there's a potential synapse.
Well, but
and that's going to be denser, right?
But potential synapses aren't. How's that useful? I guess I'm just saying. It works if you want to make three random SDRs. This whole system will work fine. If you think there's some meaning for how one drives it and the other one drives it, and there's no over, I don't know how potential synapses help there. There's potential synapses everywhere. So
exactly. So the potential. So if the top layer is activating a subset in the middle, and we want the bottom layer to learn some associations with that. If the top one is keeping those cells active while the bottom one is active, if there's potential synapses, then it can learn an association too.
Right. But the premise started off is that the top one's invoking some and the bottom one's invoking some, and you want to keep the ones that are in common. And I'm pointing out that doesn't work.
Not the ones that are in common. But not the ones that are in common.
It will form an SDR that is just some from here and some from there. It's just basically whichever is strongest.
Some from here, some from there is an overlap. That doesn't make any sense. So it's like, what's the point of that?
It's not an overlap. It's a subset from both of their kind of
and then that
forms the new SDR.
Right, but that's random now. I mean, as far as I'm concerned, it has no meaning. It's random.
It's based on
it's informed by both of these, isn't it?
Yeah.
Well, what would it do? You say it's informed. So let's say, and don't forget, we have to do this over many columns, not just three, right? We're doing this over many, many columns. And so if I did over many columns, I can't even say, half are from here, half are from there. Let's say I have 100 columns and there's only 100 cells active. One cell from each column that's voting. I mean, it just doesn't work.
Maybe like an example of how that could be useful is, let's say the top one is like context, like in Ramy's example, the fruit bowl. And then
now we're not talking about voting now, right? Now we're talking about inner column.
Yeah.
Let's not jump around. If we're going to be talking about let's talk about voting IDs, layer 2-3 to layer 2-3 type of things. If you want to talk about the fruit bowl, I didn't agree with that diagram about the fruit bowl. I didn't think that was. I would have drawn that differently. So here we're talking about voting IDs. We're talking about what kind of knowledge can be transferred from one column to another. And I've always argued that when you have an SDR, a truly sparse 2%, let's say, that there's no way that the overlaps between those can be meaningful. And so I think that surfaces here too. In this case, you could say, I have 3 columns, 2 are active, 1's not active. I'm going to pick 50 from column above and 50 from column B. Okay. Whether that's useful, and I don't know, but in reality, I might have 100 or 1,000 columns that are doing this all at the same time, and then it becomes meaningless. And I can't.
Well, so you can imagine in some sense that like top layer is providing a
I guess a seed for the middle SDR that's being formed. So that middle SDR is a subset of two SDRs. It's not an overlap. It's a subset of two SDRs. And that top layer is kind of providing a seed for part of those. Now, if you imagine you're learning another representation, and that same layer in the top is active, that means that same seed is going to be part of this new SDR that's being learned in the middle.
But wait a second, but these are voting columns, right? These are voting. So if it's a new object, you can't have the same seed. You got to have a different seed.
Yeah, I'm not clear on the connection to voting, but yeah. Anyways.
I mean, look, I think we have to look at. I'm not against this idea. All right, I just think we have to be. We don't want to be sloppy in our thinking about it. So if we're talking about three columns that have layer 2, 3s voting on each other, that's what I'm talking about. If we start going, oh no, one's hierarchical, or one's within a column, then we have to think about that problem separately because those are different issues. Maybe it'll work differently there. I don't know. But here,
in my mind, this problem here, the way that this is a generalized solution for any layer that's receiving inputs from any other layer at the same time, like simultaneous inputs. So it would be happening here, and I have some arguments for why I think it would be happening here in layer 4.
In layer 4, we got mini-columns. We have to include mini-columns. There's no way you're not going to include mini-columns. So it can't be happening in layer 4 the way you just described it. The way you just described it, you said we're not going to use mini-columns. You're just going to use a spatial pooler to create an SDR. And so you've tossed out mini-columns. Here, you can't toss out mini-columns. They're there. We know they're there. We have the whole mechanism for them. So now you could argue that maybe which cells you select within a mini-column might not be random. And I'd be interested in that conversation. That's all right. But I can't just slide into the layer. This is happening in layer 4 without talking about mini-columns and what's going on there.
No, I agree. I expected that.
I just feel like if I got, like, I don't know the answer to this, but I just don't see how this. I'm trying to point out why. Okay, you can say 3 columns, maybe 2 are each is providing 50 cells, and somehow it's the union or the joint of those 250 cells. But that doesn't work for multiple columns, many columns, and so it's I don't know. It's just hard for me to. Yeah, I don't see how that's going to work. I'm not against the idea. I'm just saying mechanistically, I don't see it. And I'm open to ideas how it could work. But we're going to poke holes in the ones that I see it already. So it's just because that's our job. And
this idea it's mostly intuition for me. Like again, I don't have any simulations or anything to show that this is what would happen. That it will be stable after we do. After we go over the object or what would actually happen in the layer 2.
Well, it's stable. I mean, look, we do want layer 4 to be stable, and we have that in our models. At least we did at one point, where you want the layer 4 representation to lock on to if it's got enough support to lock on to the right answer or to a single answer. So you want the recurrent stuff in layer 4. You also we knew that layer 4 could learn sequences, and that those recurrent connections will do that too. So you want it there. And you want the recurrent connections in layer 2, 3 because you said yourself you want to you want to remember these SDRs. You don't want to be off by a few bits just because you want to remember them, and so you want to lock onto one of the SDRs or the other. So those we want. It's just this multi-column voting part that's problematic for me.
Yeah.
And again, let me point out our own holes. We were just suggesting that somehow these inputs to layer 2, 3 could force a particular SDR in layer 2, 3 and lock in the reference frames. And now I'm thinking about that can't work. Now I'm thinking about it. Maybe a different mechanism is happening down to layer 6. That the layer 6 to layer 6 connections locking in reference frames. Anyway, so I don't have the answers here. I'm just pointing out that I'm going to be forceful about pointing out the holes.
No, this is not a concrete proposal in any way.
Right. But the mechanisms have to at least work. or be somehow for us to consider it further. So maybe there's a way of doing it. Again, I'm interested in are there mini columns in layer 2, 3? That's an interesting idea to me, because I never liked the idea that we just chose random. Just never, it just felt a little odd.
I don't know. It feels to me like the temporal memory would either be in, like, where are we storing the context? Is it in the layer 4? Or
what do you mean context? Storing what context?
So temporal memory, what it will do is that it will, as we move from one feature to another, it will basically store like the history of these observations, or not store, but like
no. Let's be careful. The temporal memory does two things, right? If there's a sequence, a repeatable sequence like a melody, or like a learned behavior that you do over and over again, yes, then the temporal memory will learn the context will be the previous elements, a series of elements in a row, right? That would be a context. But in the morphology models where we don't have that temporal component to it, the temporal memory, what it will do is it will say the context, here's a feature, I'm going to represent it uniquely in the context of this object at this location. That's what it does. So the context is you have a feature which you've seen multiple places in the world, and now you represent in some particular context. You need a unique representation for that. So that's what's happening in layer 4.
But do you need sequence to represent that, or just projections?
No, sequence. It could be in the context of the location on the object from layer 6, that's a unique context. Saying, oh, I'm on this corner of the mug, therefore I've learned that this feature is represented uniquely at this corner of that mug. Or it could be I'm at this sequence in a melody, and so I have a unique representation of my location and time in the melody, where I am in the temporal sequence, and that would be the context. In both cases, you have a unique context in which you're representing the feature. It doesn't have to be time. It could be just the location on the object, which is coming from layer 6, which is determined by the movement of the sensor, and that's the whole thousand brains theory, right? It's that would be the context. In the context, just think about border ownership cells. In the context of the tiger on the rear leg, I expect to see this feature. I can see that same feature someplace else in other objects, but in the context of a location on a particular object, that feature is expected. Or it's the logo is expected, part of the logo is expected on the mug at this location on the mug, but the logo could also be on a hat or on a t-shirt or something else.
So if there's temporal dependency between the features, then we would be using the temporal memory to provide.
Right. If it's there, we use it. If not, we use the location information, or both, whatever it is.
Yeah.
That was sort of like the big extension from temporal memory to the thousand brains theory, is that in temporal memory you have unique context through time, the sequence, and then the extension with thousand brains is that the context could be the unique location in on the object, and the layer 4 cells don't know the difference between those two. They just here's your SDR.
I don't know what the mini columns will do in layer 2 and 3.
Well, that's the question. I was hoping maybe we'd have some ideas about that.
Yeah, Tristan, you had a question. I don't know if before starting on that.
Oh, sorry, no, man.
Oh, okay.
Yeah. What's interesting, if you look at these double bouquet cells, they span layers. They seem to be in all layers. I don't remember if they project up into the upper layer 3 and 2. I don't remember that. For some reason, I thought they didn't.
And I mean, wouldn't we kind of want a different double bouquet cell anyways, or like?
You would. So it is weird, and so but there are multiple cells. They're not all in one layer. So, it's
because you don't want the mini column to be defined by
right. You're absolutely right. You don't want the same mini column meaning in layer 4 as you have in layer 6. So that's a little mysterious. But the challenge, what it does appear, is that the mini column acts as a sort of it's kind of a unit. and there's different double bouquet cells at different points along the different layers, but they do send dendrites and axons up and down the over multiple layers, not all layers, but over multiple layers. And so they're somehow coordinating some parts of the different layers, or seem to be at least impacting each other. I don't know. I can't say anything further than that. No, but you're right. We don't want there would be a separate set of bouquet cells, and I remember them being at the bottom of layer 3, and therefore they would influence maybe layer 4. And then there's some others in the lower layers, I believe, and they could be influenced in layer 6 or something like that in layer 5. So who knows? There's a lot of, this is not a very heavily studied area. But so I think, and we have enough information to suggest that each layer could have its own meaning for mini columns, and yet they still somehow, somehow they're tied together. I don't know how that works. I don't understand that. It's a mystery to me. So who knows? Also, if a double bouquet has an axon, and even if the axon only branches locally, like the mini column, they could be impacting neurons in other mini columns farther away, which send their dendrites over there. So just because they project locally to the mini column doesn't mean their impact is only local. It's just like very suggestive. Remember, Mountcastle actually said the unit of replication in the cortex is not the cortical column. He said it was the mini column, and then he said mini columns are grouped together in columns, and then they work together in a column. But his language was the unit of replication, the unit of function is a mini column. So that's confusing too. Anyway, I don't know.
That kind of makes sense, because like a mini column towards the end of on the border of a column would get overlapping sensory input from.
Well, he would argue not. He would argue that all the mini columns in a column all are processing the same sensory input, and then you have an abrupt change to the next column.
So
that's the argument. That's what his papers defining the column were. Just to throw out a few things here. Like layer 5 is, if that's a motor output layer, which we think it is, you would expect it to have many columns, because you would expect it to be taking some sort of a generic output. Well, actually, sort of the inverse mini column. I'll take that back. Anywhere you think you have to take a common representation and turn it into a unique representation, you need the mini columns. I've speculated that there's mini columns. We know there's mini columns in layer 6. And I've said, maybe those mini columns in layer 6 are taking a grid cell representation and turning into a unique grid cell representation in the mini column of layer 6, so that you'd have unique location IDs. Anyway, this is very speculative, or contemporaneous stuff here. All right. Well, it would be, if someone ever comes up with a theory why we want mini columns in layer 2, 3, I'd be very interested in hearing it. I've never been able to think of anything. So
I don't know if this figure is helpful, but
there you go.
The kind of cleanest drawing.
Right, and some of these are, which are the yellow ones? Are the yellow ones the bouquet cells?
Yeah, unfortunately, the figure caption is far away from the figure, so you have to.
I think it was the yellow ones. Yeah,
so spiny neurons in layer 4 are green, pyramidal cells are red.
Pyramidals are green, spiny for gray. Double bouquet cells are black in 2, 3.
Yeah, so those.
What about
here?
What about the other double bouquet cells? They don't talk about the other ones.
Well, they say they reach. So they say double bouquet cells of layer 2, 3 are distributed so that there's one such cell for each pyramidal cell module. The horse-tailed axon of the double bouquet cell runs alongside the clustered apical dendrites of the layer 5 and 2, 3 pyramidal cells. And then
right, but I've read that there are other double bouquet cells not in layer 2, 3, so they're just showing the ones in layer 2, 3.
Yeah.
But this is so you can see here, if you believe this diagram, those cells, they show those black cells only extended to layer 4. They don't show them going anywhere beyond layer 4. So that's our theory, right? Now this is layer 4, so you got multiple layer 4s here, but the basic idea is that these would be defining the mini column activity in layer 4, not in layer 5 or layer 6. It's interesting, they also go up to at least part of layer 2, 3. So that would suggest that maybe they're creating some mini column representations in layer 2, 3. It's the same ones.
Suggest they would be the same.
Same, right? So yeah, so maybe we should think about that. Like, okay, if they're the same, what would it mean to have a mini column in part? Not you see, it doesn't go all the way up. It doesn't go to the top of the column. It goes part of it. So what would it mean to have some mini columns in layer 2, 3 that are having the same basic mini column base is in layer 4? I don't know. But there are other. I believe there are other. There are mini columns in layer 5 and 6, and I believe there's other double bouquet cells that they've shown down there.
I guess you could imagine that based on what features tend to be active for a particular object, that might bias what cells are form the kind of output, like the pooled SDR. So I don't know. Just thinking, like, if you see a letter that's formed of a lot of, 45-degree edges, proportionally to another object that's formed by, let's say, like a cross versus a multiplication sign.
Right.
Assume they're learned as different objects, not rotated versions. So they have different features that tend to be active, and therefore different double bouquet cells. So there might be less overlap in what kind of cells tend to be active in the output in that layer 2, 3. Whereas, let's say you have a H now you're learning, that's going to have more overlap with the plus representation in 2, 3.
Maybe I'm getting lost. I need a picture with all these features. I'm having trouble visualizing. Because we're talking about a point on these objects, right? Like a part of the line or something like that.
Yeah. So at any given look, so let's say you're looking at, like, you're learning. If you look at my screen, like, you're learning the plus.
No, I wouldn't say I'm not.
Oh, sorry, not my screen. My video.
Yeah, your hand. Okay, right, there we go.
If you're learning a plus versus you're learning, like, this multiply.
Were you saying learning? Is that the feature I'm detecting, or you're saying that I'm learning an object?
No, the feature you're detecting is either like a 45-degree line, right, or 115 or whatever, or you're recognizing 90-degree and 180-degree lines or whatever. And let's say those are activating different double K cells, different mini columns in L4.
Different mini columns, right?
But then they might bias when the temporal pooling is happening in L2, 3. That could bias which cells are kind of the winners, or kind of are pooled for that.
It would change what the winners are. It would force them to be different.
Yeah,
right.
But then I'm saying, if now a H comes along,
yeah,
that would have more overlap in the output representation in L2, 3 with the plus, because of the greater overlap in the features that had kind of composed it.
Well, but I'd argue that it wouldn't. And the whole point of the temporal memory is the following: you can have the same feature in different contexts. It would be completely different SDRs. So
but it would be the same mini columns.
Same mini column, but no one looks at but the actual cells.
I guess I'm just wondering whether the mini column would bias which. I don't know if we want this, but you're just asking for a potential.
Right.
Like, what could that do? And I'm just thinking it could bias which cells win in L2, 3.
So we walked through the simple math on this once before and saying, okay, the same feature occurs in different contexts many, many times. Like imagine if your features are one of 12 intervals in music, right? And so I've learned hundreds of melodies, and the same intervals occur over and over and over again, these different melodies. And each time I have the same interval, I have to have a unique representation for it, completely unique. Not over. I don't want an octave in, or a major third up in one melody to have any overlap with a major third up in another melody. There's no. I don't want that. I want them completely different because they're completely different melodies, and so you can just walk through the math. Although the major third up is going to select the same mini column. So, but if you say, I have 15 cells per mini column and I have so many mini columns active, and I randomly choose, one of the 15 cells, you can show that the overlap is never going to be anything significant. It's like I was worried the opposite. I was worried there would be overlap, and there isn't any. There's no. Yes, it's more likely, but statistically, it's never going to be enough to be meaningful. So it's the opposite. It's like, yeah, even though you're biasing on the same mini columns, it seems the SDR you get out of it has no. You can't extract anything from it. It's like it doesn't seem that way. I don't know. You could associatively link cells in the mini column with another cell in the mini column another area. You know, if you went back to that image that showed the actual neurons that Vivian put up.
Yeah.
Yeah.
By the way, just another piece of info. This is a more recent review paper. I think, Jeff, you reviewed it a few years ago. And there they note that the double bouquet cells are layer 2-3, but also layer 4 and also layer 5. So
right.
It doesn't seem just to be
you would right, and you would think that the layer 5 ones would then project down the mini comes down to layer 6.
Yeah,
so because they do stay
preferentially located in the supragranular layers.
So that means they have more of them up there. I don't know, Yeah, this stuff is so damn hard for these scientists to do. They want to say anything, but you have to be careful because they can overinterpret it. One of the things when we were starting to talk about learning behavioral model, remember originally I proposed that the behavioral model would be just in the same column as the morphology model. And so one of the reasons I proposed that is I said, well, what if the mini columns in layer 3, they would have the same orientation preference as the mini columns in layer 4, but what if they were actually driven only by the magnocellular cells, the ones that detect motion? So you'd have a feature at an orientation, but it only becomes active when it's moving. So that was one of the reasons I proposed this, because I knew there were mini columns that were in layer 3, and in this case they would be the same orientation as the mini columns in layer 4, and you could just say, well, these represent the orientation that's changing, and this represents the orientation that's static. So you could have both of those models in the same column. That's still a good idea, but we wanted to move them elsewhere for good reasons, so we did. But I just want to point out that I had an explanation for why you had the mini columns up there in layer 3, because it could be the behavioral model, in which case you need the same orientation.
I mean, also in all our diagrams, the input that we're supposed to drive the mini column activations, we always draw as at the border of layer 3 to layer 4. So that would be kind of,
that's what, this diagram shows them 3 different depths in layer 2-3, where some other scientists, and they don't show at the top of layer 2-3. So they show at the middle, the bottom, and further down. And other scientists might say, oh, they're at the bottom of layer 3. I don't know. It depends on what cells they stained. Depends on how much coffee they had that morning. I don't know what it was. These are impossible things to determine in some sense. Different animals, different gestation ages. Who knows? Remember, all these cells actually moved during the growth of the brain. They all move up through all the columns. They actually migrate from the bottom up to the top. And so sometimes they do these studies at different gestation ages. There's a preference to like to do them right around birth, in which case those movements haven't necessarily finalized. And so you have to be careful about that too. And all these crazy things to think about. But I think it looks like there's mini columns in layer 3 and layer 4. They seem to have the same preference, orientation preference. That seems to be a fact.